Hello everyone, I'm Huan Zhuowu from Deutsche Telekom Chair of Communication Networks, TU Dresden. So today I'm going to demonstrate how to implement network slicing in a software-defined network so that the isolation of network resources can be realized. The goal of today's presentation is to show that the different requirements can be fulfilled on a shared physical infrastructure by network slicing. So the presentation will consist of two parts. First, I will go through the basic concepts of network slicing, including what is network slicing and how the architecture of network slicing is. And secondly, I will go in details to show how to realize network slicing in our CompNet emulator step by step. Now let's go to the first part, network slicing concept. So as we all know that network slicing enables the definition of multiple virtual networks on a single physical network infrastructure. Also, each network slice is created to meet the specific requirements of a set of applications and services. Additionally, a network slice is viewed as a logical end-to-end network that can be created dynamically. So, in one word, network slicing enables multiple services with diverse application requirements to share available networking infrastructure. So, in order to realize the network slicing, basically it needs two parts. First is an isolated subset of available virtual resources. Here, the virtual resources normally are, for example, topology of the network, traffic, bandwidth of the networks, and so on, so that the applications or services can be run on top of such isolated virtual resources. And second part which is needed is that a set of rules for identifying the traffics that we run on those slices. So basically in our implementations, we will follow these two steps to implement our network slicing applications. Next, let's see the architecture of network slicing. So basically, three components need to be employed to realize the concept of network slicing. So the first part is that the virtualized infrastructure platform. This platform provides the virtual resources which can be isolated for different slices. A second component is network slice instance. Basically, this part is our network functions. And the third part is network slicing management. This component is the main component of the network slicing. It's the responsibility here is to manage the traffic and also to isolate the virtual resources. Basically, we will implement these three components so that the network slicing can be realized. And in the following implementations and examples, so our CompNet emulator provides the virtualized infrastructure. We will use the SDN controller to be a network slice management. Also, we will use like iPerf or the pin tools to generate the traffics as a network slice instance. After reviewing the concept and the architecture of network slicing, I'm going to show the two examples of implementing network slicing. They are topology slicing and service slicing. So the following steps will be: first, I will show the network that the network slicing will be run on top of it, and then two examples. In each example, we first will go through the task and then step by step how to implement them, and in the end I will show 3 ways how to verify the network slicing. A multi-hop network as network infrastructure is used for 2 examples. The network is shown in this figure. There are 4 hosts from H1 to H4 and 4 SDN switches which are S1 to S4. These 4 switches are also connected to one SDN controller. And now let's log to our CompNet email and build this network. So on the right side of my display, it's a terminal which is already logged into our CompNet email. And the right side, it's a network which we are going to build. The example code stays in the folder of CompNet email app realizing network slicing. Now let's see how it works. Basically, it's very simple. According to the network states on the right side, the 4 hosts and 4 switches are created, and they are connected by the virtual Ethernet cable that allocate 10 megabits and 1 megabit bandwidth respectively. After the topology is loaded, the switches are set as open-way switch supported. The MAC address of each host is set according to its IP address, and additionally, all pair of ARP entries are used to remove the need of handling broadcast. In the end, a software-defined network switches are configured to connect to a remote SDN controller C1. The IP address of the controller is following, and on the port of 6633. After we start the network, then the whole network is available for our network slicing examples. After building the network, so we can start to build our examples on top of the network. The first example to be implemented is the slicing of network topology resources. The topology resources will be isolated into 2 layers, as this figure shows that each slice has its own view of network nodes as well as the quality of connections. In such case, the S1, S2, and S4, including their connection bandwidth, are available for H1 and H3 from the upper slice point of view, which means that the rest of the network resources are not visible to these network nodes. In a similar manner, network nodes H2, H4, and also H1, S3, S4 can only be connected to each other in the lower slice. However, it's impossible to send data over other slices. For example, from H1 to H4, it's impossible to send a package between them. Now let's start to implement the topology slicing example step by step. The codes states in the topology slicing. As we mentioned before, basically there are 2 steps to implement network slicing. The first step is isolating the virtual resource, and second step is identify the traffic to the corresponding slice. Let's do it step by step. The first, isolating the resources. So in order to achieve the isolating of resource, multiple flows should be defined for each switch on each output port. In this case, the ports will be connected in the same slice, and the ports in different slices will be isolated, of course. And for instance, on the switch 1, the port 1 and port 2 are connected. This is the first flow. And second flow, it's connecting the port 3 and port 1 because these two ports are in the upper slice. And for the same reason, the two more flows connecting the port 2 and port 4 are created on the switch 1 because these two ports are in the lower slice. And also, the same principle is used to define other flows on all ports of switch 4, switch 2, and switch 3. The example codes is listed here. The meaning of the codes is that first it shows the DPID of switch, and then it's the in-port number. Once we know the DPID of switch and the in-port number, the corresponding out-port number is also given, and then the flow is connected or created. So the second step is identify the traffic into corresponding slices. And normally a traffic packet can be classified into the corresponding flows and perform their actions according to the match rule in a flow table. Here in the network, SDN network, there are several key parameters we need to define. First is the match. The second is the action. So let's see how we implement this in our examples. The example codes is in the function of packet in handler. Normally, the controller first detects the new coming packet by the source switch ID and the input port. This forms a match to ensure that the packet is associated with the correct flow. So based on this information, we get our first key parameters in the flow table, which is match. And then, based on the defining slice in the previous step, an output number can be looked up for the packet. The forwarding of the packet to the selected port is the action of this packet. So after this step, we will get the second parameter in the flow table, the actions. After getting the actions and matches, a flow entry can be created in the form of tuple, including the data path, match, and actions. And this flow entry is sent along the packet to the flow table on the source switches. Once it's finished, then the new coming packet can be performed according to the requirements in the corresponding network slicing. And then the implementation of the two steps in network slicing is finished. The next, we will see how we can run these examples and how we can verify the implementation of our example. So after implementing the example, let's run this example and then verify the functionalities of the slices. So how to run this example? First, enabling the controller to load the application. Basically, here in the emulator, we use a real controller. So we need the real manager to run our implementations, which is the topology slicing. Now it shows that the application is loaded. And in the another tab or the terminal, we starting our network with mininet. So we use a Python 3, and the network is the one we created beforehand. Now the network is loaded, so we are going to use 3 ways to verify the functionalities. First is the pin. So the pin, we use it to verify the connectivities of our slicing. Normally we pin all, and then the expected result is that the H1 and H3 can be interconnected, and H2 and H4 can be interconnected. Meanwhile, H1 to H2 and H4 and H3 to H2 and H4 are impossible to be connected because they are in 2 different slices, and these 2 different slices are isolated. So basically it shows that it's already show our result. First it's from H1 to all the other 3 hosts. The result is that H1 can only be connected to H3, and also the same thing, the H2 can only connected to H4 because H1 and H3 are in the upper slice and H2 and H4 are in the lower slice. So it shows the isolation of the slice, and also through these pin tools we know that the connectivity it works as we expected in our example. So the topology of the network is sliced into 2 parts. Now the second thing is that we check the bandwidth, because in the upper slice the bandwidth is 10 megabits per second and the lower slice is 1 megabit per second. So in order to check the bandwidth, we use a tool, the name is iPerf. So first we check the bandwidth in the upper slice, if it's 10 megabits or if it's 1 megabit. Because if the slice is successfully isolated, then the interconnection between H1 and H3 can only be 10 megabits. It's impossible to be 1 megabit. So let's say it. So iPerf from H1 to H3, it generates the TCP traffic between the H1 and H3. And let's see how big is the bandwidth. So it shows that the bandwidth it's 10 megabit and 7.96 megabit. Basically, it shows that the connection is in the upper slice and the connection is impossible to the lower slice. So also the same principle between the H4 and H2. So the bandwidth between these 2 hosts, it must be 1 megabit. If we implemented it correctly, it shows that it's correctly. So based on the iPerf, we can verify that the bandwidth of these 2 slices are correctly implemented or correctly sliced. Now a third way to verify the functionality of slicing is we check the flow entry. So the tools here we need is open switch control, open flow controller. The command is first we show that the open switch on the open flow using the open flow controller. Let's say for example we just check the flow entries on switch 1. So we see how the switch 1 will handle all the incoming packets. So here it shows the flow entries in the S1. So for example, if there's a packet come into the port 1 on the S1 in this figure, so we must know that this packet is in the upper slice. So the expected output is S3, it's port 3 on switch 1. We see that the output is port 3 on S1. So it shows that it doesn't go to port 4 or port 2 on the S1, and it shows that the slicing is successfully created. So the same principle here in the lower slice. If the input on S1 is port 2, then the output on S1 should be port 4 because these two ports are in the lower slice, and the other two ports, port 3 and port 1, should not be connected because they are in the upper slice. So the three ways to verify that the functionality of network slicing is finished. And then keep in mind that please stop these applications, otherwise this application will there will be the conflict between this application and our next applications. In the first example, the physical topology of a networking infrastructure is sliced. So in the second example, the logical network service is going to be sliced. As illustrated in this figure, the two types of slicing are defined. The first one is video slice, showed in the figure as the red part. The video slice is for 10 megabit per second bandwidth, and the traffic is UDP traffic with the destination port 9999. And the second slice is non-video slice, showed in this figure as the blue lines. This slice is for all the other traffics with 1 megabit per second bandwidth. So let's log into our CompNet emails. The example code is also located in the app Realize Network Slicing. And for this example, the code is service slicing. As in the first example, there are also two steps to implement the service slicing. The first step is isolating the virtual resources in the network. And second step is identify the traffic to the corresponding slice. Let's go to the first step. So in this example, as shown in the figure, there are two end switches, switch 1 and switch 4. So the two flows are defined to the destination hosts on these two end switches. And S1, a flow on output 3 goes to the destination MAC address of host 1. And same principle, a flow on the output 4 goes to the destination MAC address of host 2. Also, the UDP port number is defined as 9999 to identify packets in the next step. We give these two slices the slice ID. For video slice, we give the slice number 1, and for non-video slice, we give the slice number 2. So, and the S1 and S4, the video slice number 1 is assigned to the output 1 because the output 1 has 10 megabit per second bandwidth. The non-video slice number 2 get the output 2 because the output 2 connected to the 1 megabit per second bandwidth. So the same principle on the other on another end switch, switch 4. So the video slice connect with the output 1 and the non-video slice traffic connect to the output 2 with 1 megabit per second bandwidth. So in the function packet in handler, at the beginning, this code shows that how to get the information to build the match so that the traffic can be identified. And then after that, we will see how to build the action according to the incoming packet and the defined slice. So the first, we check that if the switch is an end switch. If it's an end switch, then first we say that on the two end switch, if the packet is from the middle switches, which are S2 and S4, or it's from our destination hosts. If the packet is from the middle switch, then we just forwarding the packet according to its destinations. So the output of the forwarding can be get from the defined MAC to port rulers, and based on the output, the action can be created. And second, if the packet is from the 4 hosts, the 2 switches need to classify the incoming traffic if they belongs to the video slice or non-video slice. So how to identify that? Remember the definition of these 2 slices. If the packet is UDP packet as a destination, if the packet is UDP packet and the destination port is 9999, then this traffic belongs to our video slice. So we give the slice number 1 to this packet because slice 1 is a video slice. According to the slice number and also the ID of the switch, so the corresponding output can be generated according to our predefined rules. Here, for example, if one UDP packet with the destination port 9999 comes from host 1 to the switch 1, then the switch check, okay, it's a UDP packet and also the destination port is 9999, then it belongs to a video, slice which should go along to the right lines. So the output should be the output 1. And once we know the output and also the saved parameter of import destination types, this parameter built the match parameter, and according to our looked up output number, it built the action parameter. And these 2 parameters together can build one new entry flows for the new incoming packet, and then this entry flow together with this packet will send to the corresponding switch. In our example, it's a switch 1. So for all the other packages, for example, if the packet is UDP but it's not with the destination port 999, which we know that this packet should go to non-video slice. So the non-video slice ID is 2. So based on the slice number and also the switch ID, we can get the corresponding output number. The same like the last step, we save the information of such packet as a match, and then together with the output slice number and the switch ID, we build a second key parameter action. These two key parameters built together can generate a new flow entry, which for the UDP packet but not destination port 9999 to the non-video slice. Also, other possible traffics, the same principle. For the packet of the TCP packet, it belongs to the non-video slice. Also, for others like ICMP packet, it also belongs to non-video slice. All these slices are going to go to the non-video slice, and their flow entries is also added to the corresponding flow tables on different switches. And in the end, we have to check if the switch is S1 or S3, then they just flood the output, and the job is just forwarding the incoming packet according to their destinations. So until here, the two key parameters match and actions are generated for different types of the packet, and they build a flow entry together. These flow entries are sent together with the packet to the corresponding flow tables on different switches. So now let's go to see how to verify this implementation of the network slicing. So the same tools, same ways like in previous example. We identify the connectivity with pin. We verify the bandwidth with iPerf, and then we can also check the flow entries on different SDN switches by using the OpenFlow controller. So like before, first we have to run our application. In the first step, we run our real manager, and the application code is service slicing. Here it shows that the application is running. Then we start our network. Now it's the network is started, and the application is also loaded. So first, let's check the connectivity. So based on our definition, what is our corresponding result? What is our desired result? Because the pin generates the packet which is generated by pin are not UDP packets with destination port 9999. So all of them belongs to the non-video slice, and the connection among all these four hosts should be successful. And as our result of the verifying, it also shows that the connections among H1, H2, H3, and H4 are all successful. And then let's verify the bandwidth. Here I will give the example how to verify the bandwidth between the host 1 and host 2. So I'm going to generate video service traffic that is 10 megabit UDP traffic with a destination port 9999. So the service should use the video slice. So first we have to log into host 1 and host 3. The tools we use here is the Xterm. We open two terminals on H1 and H3. So hopefully you can read the terminal. So in this verification, we use H1 as our receiver. So here, use iperf, set the S3 as the receiver host. Here, server, and it will listen to the UDP packet and to the port 9999. We give the bandwidth of 10 megabit. Now the S3 is listening on UDP port 9999, and on the S1 we use it as sender, so which means it's also the client. So we use iperf to set it as the client, and the destination address is the IP address of host 3. The traffic which is going to be sent is UDP traffic with the port number 999, and the traffic is 10 megabit, and the sending is in the time interval of 1. Now it's sending that. So the result shows that the H1, our sender, it keeps sending video traffic, and host 3 is able to receive the video traffic with the bandwidth of 8.71 megabit per second. It means that the video traffic uses the video slice which we already created. So it also, in this figure, it shows that the traffic between the host 1 and host 3, they are using this slice because they are the video traffic, so they use the video slice. They don't use the lower one, the blue path, because the blue path is for the non-video traffic. And the third way to verify our implementation is use the open flow controller. So on the open flow controller, it seems like in our last example. So here, for example, we check the flow entries on switch 1. So we show the flow entry by using open switch open flow controller, and we check the flows on S1. So this example, all the flow entries on S1 is printed in the terminal. So for example, we check like, for example, if here they get the first flow entry, we check that on the S1, if there's a packet come into the port 3, it means it's coming into this port, and the destination of this packet is 3, or it's a host 3. So the destination port is 999, and also it's a UDP packet, which means that this packet belongs to our video slice. So the corresponding output port should be port 1. So here it also shows that the output is S1. It's port 1 on S1. And for the others, for example, the second flow entry, this is a packet, but this packet is not UDP with destination port number 999. So it just it goes from the import number, it goes to the host 2. So the corresponding output it's port 4, no matter if it's use the blue connection or the red connection, because they are always using the same Ethernet cable. So another flow entry, for example, this flow entry, the flow entry identify the incoming packet, which is the ICMP packet. So this packet belongs to non-video packet. The incoming port is port 3 on S1, and then it should go along the blue connection. So the output number is port 2 on the S1, because this ICMP port it's in the non-video slice. So in this case, the network can identify different types of the incoming packet if this packet belongs to video slice or the non-video slice. Based on the slice, the corresponding output port can be generated, and then all this SDN switch knows how to handling the new incoming port, so that the requirements of different traffic flows can be fulfilled. So the third example is also doing the same job as in example 2, the service slicing, but in the example 3, SDN proxies is used. Because of the system supporting, the SDN proxies have to be created in a Docker container. So after you get to know how to use the Docker container, then the example can be implemented. This can be left as an exercise, and more detailed codes and explanations is in our computing book. So thank you very much.